Okay, so today we'll talk about randomization tests, and okay, well that's what we'll talk about. All right, and so before we get into randomization tests we can think of them as kind of the computational way of performing hypothesis tests. And so perhaps this requires a bit of a review of hypothesis testing. Okay, and so I know many of you have taken Stats 10, and I also know that many of you have not taken Stats 10. That you guys took some kind of other course that was deemed equivalent, you know, either prior to you're entering UCLA or something, and so maybe we're not all on the same page regarding hypothesis testing, and so this will just serve as a brief review, and it'll just to make sure we're all on the same page here. Okay, so when you do hypothesis testing, you know, you create a null hypothesis and you create an alternative hypothesis. And the null hypothesis is going to be along the lines that there's no significant difference between populations, or that whatever we observe in our data is just a result of random sampling. Okay, so so we set that up with our null hypothesis. So, you know, if you're talking about population means, it's going to be, the null hypothesis is that the mean of population 1 is equal to the mean of population 2. Or if we're talking proportions, it's going to be the proportion of population 1 is equal to the proportion of population 2. That these, if we're comparing populations, the null hypothesis is going to be that the two populations we're comparing don't have any difference. We also, during the process of doing a hypothesis test, is we go and we calculate something called the p-value. The p-value is a probability, and it's the probability of observing our data, or something more extreme, if we assume that the null hypothesis is true. Okay, so, you know, when you take so maybe your null hypothesis says that the two populations have the same proportion. Okay, that's going to be your null hypothesis. When you go out and collect actual data, you get the sample from population. Sample 1 has maybe a proportion of 30%, and sample 2 has a proportion of 35%. Okay, well, 30% is not equal to 35%, and the question is that difference of 5 percentage points, is that something unusual, or is that something completely mundane that could have happened just from random sampling? And so the p-value is the probability of getting a difference of 5 percentage points or something more unusual, if we assume that the two original populations have the same proportion. Okay. And I know I've just been kind of talking, and there's 2 sentences up on the screen, but I'm hoping these concepts are at least kind of familiar to us, okay? Because we're just kind of trying to jog your memory here, all right? So here we've got just an example using population means. The null hypothesis will be that mu1 is equal to mu2. And let's say we go out and we collect data, and this time we get x bar 1 Sample 1 has a mean of 10, and sample 2 has a mean of 12, right? So we have a difference of 2 points. Is that difference significant? Okay, and like everything in life, the answer is it depends. And in this case, it depends on the standard error, right? You guys remember what the standard error is? What's the definition of the standard error? It's the standard deviation of the sampling distribution. And what is the sampling distribution? It's the distribution of all possible sample statistics, right? Drawn from said populations, okay, under a certain criteria. So you know, we want to know is that difference of 2, is that large? Well, it depends on what the sampling distribution looks like and how much spread, or what's the standard deviation, or what's the standard error of that sampling distribution, okay? And so in one scenario, that standard error could be very small, okay? And so maybe the observed difference of 2 is much larger, maybe like 5 times larger than the standard error, okay? So in this case, we would get like a t-score of 5 or something like that. And in that case, we would say the difference is significant. You'd look up that t-score in your table or do some other math and get a p-value. You get that difference is significant. Difference of 2 is significant. On the other hand, it's also possible that the standard error is large, and maybe the observed difference of 2 is not much bigger than the standard error. Maybe it's only 1.2 times bigger than the standard error. And in that case, this difference of 2 is not significant. And so, and these are the kinds of conclusions that, based on the conclusions that we might, this would affect the kinds of conclusions we might make, right? And so when we're talking about p-values, rather than just saying the observed difference that we got, 2 points, is that large or small compared to the standard error, we will often do something to look up a p-value. And our p-value is just a way to quantify this, this concept of the probability of observing our data if the null hypothesis were true, okay? So if our p-value is tiny, it means that the observed difference that we saw, that was so large that it's very unlikely for us to get these results just from random chance, right? So a tiny p-value means, yes, technically it's not impossible to get this result, but it's very, very, very unlikely to happen. So we're going to conclude that it wasn't a result of random chance, and rather something else is going on, okay? But if the p-value is large, it means that the thing that we observed in our data is quite probable to happen even when the only source of variation is random chance, okay? So that doesn't prove that the null hypothesis is true, but we certainly don't want to eliminate the possibility that our data is from random chance, okay? So, it'd be like if you flip a coin 100 times, you would expect to get about 50 heads and 50 tails, okay? If someone gets 95 heads and 5 tails, is it technically possible to get that kind of result from random chance? Technically it's possible, but it's so incredibly unlikely. We call it, it's practically impossible. It's probably on the order of like 10 to the minus 15 or something. I don't know, something very improbable to happen, that we would say, I don't think we got this result of 95 heads and 5 tails from random chance. Something else has to be going on, okay? On the other hand, if we get 55 heads and 45 tails, we say, you know what? It's not exactly 50 heads and 50 tails, but it certainly could happen just from random chance alone. So it doesn't prove that the coin is fair or anything like that, but it just means, you know what? You tell me that it happened by random chance, I have no reason to dispute that, okay? And that's what we're going off of. And so these things, when we did that, they use the normal distribution, or the t-distribution, as part of the way we get our p-values, okay? And they depend on the central limit theorem, and maybe you have to prove that in 100B or something like that. And so because the normal distribution and the t-distribution, they're defined by parameters like the mean and the standard deviation, we call these parametric tests, okay? And in order to use these tests, we often said you've got to check conditions to make sure that you can apply the central limit theorem, right? Do you guys remember what those conditions were for using the central limit theorem? What's that? N greater than 30? Okay, yeah, that's a rule of thumb for having a large sample size for means, right? And then if we were dealing with proportions, we have the same condition, large sample size, but It's not n greater than 30, it's what? At least 10 successes and at least 10 failures, so n times p is over 10 and n times 1 minus p is over 10. Okay, so that's one of them. Large sample condition that has to be met. What else has to be true about our data? To use the central limit theorem. Randomly selected, yeah. So we want to make sure that our data is randomly drawn from the population and every observation is independent of the other, okay? And going along with observations being independent, you know, our population has to be large in comparison to our sample, right? If we're sampling too much of our population, then our observations are no longer independent of each other. So yes, so we got the random and independent. Our samples have to be large. And if we're sampling without replacement, our population needs to be large compared to our sample. Okay, so those are your parametric hypothesis tests that depend on the central limit theorem. Today we're going to take a look at randomization tests. Right? And in a randomization test, it's still a hypothesis test. We've got the null hypothesis that there's no difference between group means, or maybe no difference in group proportions, something like that. The key difference here is that the randomization test does not depend on the central limit theorem, okay? Instead, it uses actual randomization. We're going to use the computer to be our source of randomization, and so this can be done computationally. And the key assumption for a randomization test is that the data exhibits this property of exchangeability. All right, and we'll talk about that in a moment here. Okay, so we no longer have to have you know, the conditions for using the central limit theorem. Those no longer apply. We have this assumption of exchangeability. Okay, and if we've got the assumption of exchangeability, we can do a randomization test. Okay, so before we get into that, maybe we should talk a little bit about data collection. And we're going to use this same example. It's a silly example, and we're going to revisit it 4 times, which maybe is overkill, but just to drive the point home here. Okay, so let's say a dentist wants to know if taking 500 milligrams of vitamin C every day, if that's going to help result in having fewer canker sores in your mouth, okay, than taking no vitamin C. So this is a question that the dentist has about people's mouths and vitamin C, and is there a relationship? Okay, how we get the data, it matters. All right, so scenario 1, we're going to say the dentist, working with the local dental society, convinces, and I don't know how he does this, or she does this, but convinces all of the dental patients in town with appointments in the first 2 weeks of December to be subjects of a study. So we would say, okay, look at your calendar for the next 2 weeks. Get everybody to participate in our study. Okay, and then we divide them into 2 groups, those who take vitamin C daily and those who do not. And then we ask them how often they have canker sores in their mouth, and then we check their dental records to see who's had canker sores and things like that. All right, and then we compare the proportion of those who take vitamin C and complain about canker sores with the proportion of those who didn't take vitamin C and have canker sores. And then and I wrote this wrong, but, and we're going to say that there is a significant difference in those 2 proportions. I mean, in this case, those who take vitamin C have a smaller proportion of canker sores than those who don't take vitamin C. All right, so this is what we see. You know, those who took vitamin C, fewer of them had canker sores than those who did not take vitamin C. All right. What is our sample? According to this, how do we get our sample of patients? Well, what did we do? Yeah, it's we looked at those who had appointments in the first 2 weeks of December. So what would our corresponding population be? Yeah, well, that's the problem, is that our patients are not a random sample of any population, okay? We just said, hey, let's look at your calendar. Let's look at, you know, what day is it? Oh, okay, it's November 29th. All right, first 2 weeks of December, let's get all these people and get them to participate in our study. And somehow, magically, we're able to do that. And but this is not a random sample. So this sample does not represent any larger population. And so whatever conclusions we draw here cannot be generalized to anything else. All we can say is that, okay, well, this is what happened in our study. Okay? And if we also look at this, there was no random assignment either. This is an observational study. We just said, do you take vitamin C, yes or no? And some people say yeah, and other people say no. And so that's an observational study. So we can't make any kind of conclusions regarding cause and effect. We don't know if there's a confounding variable or anything like that. We can't make anything, any kind of causal conclusion. So all we can say is, for these patients, those who took vitamin C have fewer canker sores than those who didn't. Okay? We don't know why, and we don't know if this result would be consistent with any other group. Okay, so this is, I mean, that's interesting, but it's probably not what we want. Okay? All right, in scenario 2, we're still going to have the same, draw the sample in the same way. We're going to take the patients with appointments in the first 2 weeks in December to be subjects of our study. But this time we're going to randomly assign and tell half of them they have to take 500 milligrams of vitamin C every day, and then the other half we tell them you can't take vitamin C for the next 3 months. Okay. And then we're going to, and we look at our study, and then same results, okay? There's a significant difference. Those who took vitamin C have fewer canker sores than those who didn't. Okay, what can we conclude this time? Well, again, this time, because it's not a random sample, we can't generalize to any other group. However, the treatments were done via random assignment. So, you know, assuming that the other factors were controlled or randomized, the difference in proportions having canker sores, that can be attributed to whether they took vitamin C or not. Okay? So the conclusion that we make here would be that we don't know if this result would be consistent with another group, but we believe we know why for this group that the proportions differ. So we can say for this group that we studied, we'll come to the conclusion that vitamin C is associated with the reduction of canker sores. Okay, over here in scenario 3, we got a random sample. So somehow we have a random sample of the dental patients in town, and we get them to be part of our study. Okay, again, we're going to not use random assignments. This time it's going to be observational study. We do the same type of thing, come to the same conclusion. Those who took vitamin C have fewer canker sores than those who don't. This time we have a random sample. So how does this affect the kinds of conclusions we can make? Here, because the sample is a random sample of all the dental patients in town, we can infer that the results we observe in our study would be consistent with the whole population of all dental patients in the town. Okay, so we're going to say our sample was drawn from all the dental patients in the town, so therefore we can generalize to all dental patients in town. Okay, again, because it's observational and there's no random assignment, we cannot make cause and effect conclusions. We don't know if there's a confounding variable or some, you know, if it's because of the vitamin C, right? And we can't conclude that for the general population, meaning non-dental patients, that taking vitamin C would result in fewer canker sores or anything like that, because this was only for dental patients. But if we say that the dental patients in this town are representative of dental patients in general, then we can say, we can infer that dental patients who take vitamin C tend to have fewer canker sores than those who don't. So maybe that's something that we want to conclude. Okay. And then in our last example, we have obtained a random sample of dental patients, and we do random assignment of the treatments. Okay. We get the we look at the end of our study. Okay. So we got random sampling and random assignment, and so we can generalize our conclusion to the general population of all dental patients in town. We can also make the cause and effect conclusion regarding the relationship between vitamin C and fewer canker sores. Okay? So if we want something like that, we need both random sampling and random assignment. And that's what we have here. It's very easy for me in a classroom setting to say we had random sampling and we had random assignment. In real life, that's something really hard to do, okay? Random sampling, to begin with, is almost impossible, right? It's really hard to get a truly random sample just because, you know, how are we going to track these people down? Maybe if we're working with the dental society and we just want to get a random sample of all dental patients, maybe this is possible because maybe, I don't know, the dentists share their records of, not records, but like who their patients are, and maybe we can create some kind of master list of all dental patients. So maybe that's possible. But we have to ask, you know, we have to ask people if they consent to being part of our study. And as soon as one person says, no, I don't want to be part of your study, it's no longer a random sample, okay? As soon as one person says, I'm not interested in participating, we no longer have a random sample. And maybe for canker sores and vitamin C, maybe it doesn't really matter. But if your study is related to things that could be associated with whether someone says yes or no in participating in a study, like you're asking questions about privacy, or you're asking questions about attitudes towards science and research, or something like that, whether they choose to be part of the study might be related to that. And so so you no longer have a random sample, and so random sampling is hard to do, okay? And then, yeah, once you have random sampling, random assignment, you know, we're limited in the kinds of treatments we can assign to people, right? Like when you do experiment, like if you become a researcher, you know, you're supposed to take some kind of oath of like, you're not going to hurt people when you do your experiments. And so the kinds of treatments you can assign to people, you can't purposely assign something that you think could be harmful. And so, you know, what can we do if we have questions about, you know, what are the negative side effects of some new experimental drug? A lot of times we have to, you know, use, scientists will use animals, okay, because, you know, we don't give them rights. And so, you know, we say, you're a mouse, we're going to just inject you with something in the name of science, or we just don't do research in certain areas because, you know, we don't know the answer. So like if you know, I have kids, but you know, if you ever become pregnant, or if you ever your partner ever becomes pregnant or something, you know, there's questions of like, you know, are you allowed to do this thing when you're pregnant, or are you allowed to take this medication? And the answer for so many of these things is, you know, we don't know, because there's no research, right? You can't, if we want to know, like, is this medication dangerous for, you know, pregnant women, we can't, in an ethical way, do experiments. We can't say like, oh, thanks for volunteering for this experiment. You're going to start taking this medication, and then if you have negative side effects, sorry, but thank you for your contribution to science. It doesn't work that way. So, you know, everything, there's just a lot of questions of, you know, we have no idea is the answer right now. And that's, you know, rightly so, but yeah. Anyway, science is hard. Research is hard. There's a lot of questions we have, and it's really difficult to be able to pull off a truly great experiment that doesn't suffer these problems of random sampling or random assignment. So, you know, in a classroom setting, we can share, oh, random sampling, random assignment, and it's necessary a lot of these times to have these assumptions in place for our data, for our mathematical things to work out. But in real life, it's a lot more difficult. Okay, anyway. Let's go back to randomization tests. All right, and so we talked about, we said randomization tests depend on this concept of exchangeability in our data. All right, exchangeability is the idea that under the null hypothesis, all possible permutations of the data are equally likely, or that any permutation of the data is exchangeable with any other permutation of the data. Okay, so that's like, I know that's a mouthful. On a practical level, this means that exchangeability applies only to experiments where random assignment has been used. Okay, so you know, if you have 50 people lined up, right, and let's say you're going to assign the first 25 to be group A and the last 25 to be group B, that the order of 50 people, that order could be randomized, okay? And so you could have any other kind of permutation of that string of 50 people, and when you say the first 25 are going to go into group A and the last 25 are going to go into group B, if every single possible arrangement of 50 people are possible, then you have basically every single possible arrangement of people or permutations of people ending up in group A and group B. Okay? And every single one of those are equally likely because every single arrangement of 50 people in the line are equally likely. Okay? So every permutation of those people or subjects are equally likely. And so that's this concept of exchangeability. Right? And so here we say if the patients are assigned treatments randomly, any arrangement of patients is equally likely. On the other hand, if we have an observational study where the treatments are not assigned randomly, okay, then the permutation of groups are not equally likely. So again, so the example I said was, you know, the first 25 will go into group A and the second 25 will go into group B, okay? Instead, if we had 50 people and we said, okay, sort yourselves into those who take vitamin C and those who don't, or those who do this and those who don't, and we say sort yourselves that way, then we will not have exchangeability because those people are self-sorting, or, you know, they're sorted via, you know, something related to their choice, and it's no longer random. Okay, and so exchangeability applies only to basically experiments where random assignment has been used. Okay, we're gonna watch a video here. All right, Mythbusters yawning. I got to stop the video because when I upload this to YouTube and I have the video in it, they say I'm